Hello everyone and welcome to this lecture on eigenvectors and eigenvalues. If you are coming from a machine learning or data science background, then you must be aware that how important it is to have a good understanding on principal component analysis. It is an algorithm which is widely used in the field of data science, and it is expected from a good resource to have a clear understanding on this topic, and it is very difficult to have a clear understanding on principal component analysis without understanding eigenvectors and eigenvalues. So by the end of this lecture, I will try my best to simplify this topic for you so that you can understand it clearly and so well that you can explain the same to others as well. So let's start with eigenvectors first. I will give you an example of a vector v, and let's say I want to multiply it with matrix A. After multiplying, the idea is to transform the vector v in such a way that it may change in its magnitude or length, but it will remain on its direction. It will not change its direction. In that case, this new transformed vector will be called an eigenvector. And I will explain this in a moment that what I exactly mean by direction. So let's take an example of a matrix X which is made up of two vectors, to be precise basis vectors, and we want to change or transform these vectors in such a way that we find their eigenvectors. So as you can see on the diagram on the left hand side, I have actually plotted this matrix which has two vectors. First is this one and second is this one, and let's say that after multiplying it with another matrix, it gets transformed in such a way that we get this figure on the right hand side. So if you pay attention, there is no changes with this particular vector. It is still the same. However, the another vector, this one, has been flipped over the axis, and after transformation these two becomes the eigenvectors for the previous vector on the left hand side. Now I understand that a lot of you will have a question in mind that as per the definition, after transformation a vector should not be changing its direction, but we can clearly see that this one has changed its direction and has been flipped over the axis. So let me clarify this for you, that every time we are talking about direction, what we actually mean is the span of the vector, the span on which it was plotted initially. So although this vector has been shifted from the positive to negative coordinate, however, it is still on its original span, which is the x-axis, and this is why it satisfies the condition of an eigenvector. To clarify your concept around span, let's consider that this vector was initially over here on this point, which is 1 point towards the x-axis, and let's say that it is 0.5 towards the y-axis. In that case, in order to satisfy the condition for an eigenvector, it can scale its length within this same direction, or it can also get flipped over its span in the opposite direction like this. So if you see, it is still 1 point towards the x-axis, and to be precise -1, and somewhere around 0.5 towards the y-axis over here, and this becomes the span for this vector, which means within this span it could change its length to any given number. However, it should not be moved from its span like this in this direction, or maybe like this in this direction. So it has to stay within its span irrespective of its length, and this is why compared to the vector on the left hand side, if it is being transformed into this point, it still satisfies the condition of an eigenvector. Okay, so we have understood eigenvectors so far, which is nothing but the transformation of a vector in such a way that it remains on its direction or span irrespective of the change in its magnitude. And now let's try to understand eigenvalues. So eigenvalue is nothing but a scalar value which is directly proportional to the change in length of the eigenvector. I will try to explain what I mean here. So if you focus on this vector, which is here on this point, even after a transformation it is not changing its length, okay, which means the eigenvalue over here is actually 1. And for instance, if we talk about this particular vector, then there is no change in the magnitude. However, it has completely flipped over its span, which means the eigenvalue in this case will be -1. And let's say that after transformation this vector is falling somewhere here on this point, then the eigenvalue will be -0.5. And similarly, let's say that the vector changes its length and position up to this point. In that case, the eigenvalue will be positive 0.5. And as a last example, let's say that after transformation, this particular vector becomes double in its magnitude. In that case, the eigenvalue will be positive 2 because it has been doubled in its magnitude. Okay, so I hope that the theoretical understanding is pretty much clear around these two topics, eigenvectors and eigenvalues. Now let's quickly jump onto our Jupyter notebook where we can see that how these things are working together. Okay, so in this cell, I'm creating a new matrix, matrix A, which has 4 elements, and then I'm using this function within the NumPy library, which is np.linearalgebra.eigen, and then I'm passing the parameter the matrix A for which I want to calculate the eigenvectors and eigenvalues. And this function actually returns us the eigenvalue and eigenvector for any given matrix or vector that we are passing here as an argument. So in the following cell, I am checking the eigenvectors for the given matrix, and this one is the first eigenvector for this vector, and this one is the second eigenvector for the other vector in our matrix. And then I am checking the eigenvalues, which I said will be a scalar number, and the first one is the eigenvalue for the first vector within the matrix, which is corresponding to the change in length, and this is the second eigenvalue for the second vector. And this is how simple it is to calculate the eigenvector and eigenvalues with the help of NumPy library in Python. By the way, if you're wondering that how to calculate the eigenvectors and eigenvalues manually by yourself on a pen and paper, which I assure that nobody is going to ask you to do in your day-to-day work, but still if you're curious around it, then I will provide a link for a video within the description box that you can check out, where you can learn that how to do it manually. But I assure you that in order to work in analytics field, if you understand that how to calculate it using a library in a given language, whether it is Python or R, then that will be sufficient enough. Moving on, in the topic of eigenvectors and eigenvalues, this given equation has to be satisfied. So I will provide a proper breakdown for you. So A is the matrix for which we want to calculate the eigenvectors or eigenvalues. V is the eigenvector, and their product should be equals to lambda, which is nothing but the eigenvalue, and its product with the eigenvector. So let's try to prove this equation in terms of the first vector of our matrix. So for this particular vector, its eigenvector will be this one and its eigenvalue will be this one. So we are going to use these three, 1, 2, and 3 in order to prove this particular equation. So here in the following cell, I'm creating a variable for this eigenvector, the first one, and just next to that I'm creating a new variable for this eigenvalue. And first let's try to calculate this value on the left hand side. So I am doing a multiplication between our original matrix and the first eigenvector, and we get this as an output. And then let's try to calculate this thing, which is nothing but the product of the eigenvalue and the eigenvector. So in the following cell, I'm calculating that as well. And as you can see, this product of our first eigenvector and eigenvalue is exactly equals to the output for the left hand side. And since these two values are equal, our equation is being satisfied. Okay, so this was the calculation for the vectors and the eigenvectors on the left hand side. And now let's try to do the same calculation for the right hand side of the vector, eigenvectors and eigenvalues. So here in the following cells, I'm creating a new variable which is representing the eigenvectors on the right hand side, which is nothing but the values we have here, minus 0.75 and 0.66. And this variable is representing the second eigenvalue. So let's try to calculate the left hand side of the equation first. So I am doing a multiplication between the matrix and the right side of the eigenvector, which is giving us this output. And then I'm calculating the right hand side of the equation, which is nothing but the product of the eigenvector on the right hand side and the second eigenvalue, and their output as well is exactly the same as the output we have for the left hand side. And before we finish, let's also have an example of extracting the eigenvector and eigenvalues for a three-dimensional array. So I'm creating a new variable here, x, which is a 3x3 matrix containing 9 elements, and I'm using the same function to extract the eigenvectors and eigenvalues for this matrix. So here in this variable, each of the column is the eigenvector for each of the vector in our matrix, and in the following cell we have 3 eigenvalues for the 3 vectors in the matrix respectively. And that is it. So I hope that you found this helpful. If you still have a bit of confusion around understanding it, I would suggest that you watch this lecture one more time, because it is a bit difficult to understand this completely at once. I also struggled a lot to understand this topic initially. However, if you have understood this clearly, then I'm really happy for you, because now you're good to go for the upcoming topics in the series. Moving forward in this playlist of mathematics for machine learning, we have topics coming in like matrix determinants, the relationship between matrix determinant and eigenvalues, and eigen decomposition. So a lot of useful things are coming up within this series. So I request that you keep on following the tutorial, and please support the channel by dropping a like below and subscribing to the channel. I will see you in the next lecture. Thank you very much for your time today.